Good morning, all. Welcome back to an interesting session for basic forces or for basic interactions. So, here we will study the four basic interactions or four basic forces. In classical physics, we have studied the force is something that affect the motion of a body. That can either accelerate or decelerate or stop the particle like that. But in particle physics, the force has a totally different meaning. The force or interaction is the cause of every change, reaction, creation, or disintegration. Now we will discuss the four fundamental forces in their historical order. First, the gravitational force. We all know that the gravitational law was conceived by Sir Isaac Newton in 17th century, that is in 1680s, and it says that every pieces of matter in universe attracts each other with a force F is equal to g m1 m2 by r square. That is, this attractive force is proportional to their masses and is inversely proportional to square of their distances. And this g is the universal gravitational constant and is equal to 6.67 × 10 to minus 11 Newton meter square per kilogram square. In 1915, Einstein formulated the general theory of relativity. As per it, the Newton's gravitational law is a part of this more general and complex theory. So, the more general theory is the general theory of relativity. The gravitational law is only an approximated law under this general theory of relativity. So, the predictions of the general relativity, like deviation in Mercury's orbit, influence of the gravity on photons, and the gravitational lensing, these all predictions were experimentally verified later. And this cannot be explained using old Newtonian mechanics. Like this influence of gravity on photon were confirmed in 1919 during a full solar eclipse, and we can see a lot of images of gravitational lensing, where this gravitational lensing is nothing but a heavy object acts like a lens, since this bends the light from different stars or like that. This acts as a lens do. That is why this is bent, and an image is formed on the other side of the lens. The gravitational interaction is the feeblest force in nature, the weakest force in nature. The force carrier is graviton of zero mass. It has zero mass with spin 2. But fortunately, since the carriers have zero mass, it can reach anywhere in the universe within no time. Without taking any time, they can reach anywhere in the universe. That is why the gravitational force has infinite range. The graviton is affected solely by the gravitational force. No other fundamental force affects the graviton, and the strong force does not affect, the electromagnetic force does not affect, The weak force does not affect, only is affected by the gravitational force. One of the example for the weakness or the how feeble the gravitational force is. Earth emits the gravitational wave with a power of 10 watt, only 10 watt, while circulating the sun. So this much lower power is emitted by the earth while circulating the sun in the forms of gravitational wave. And as per the theoretical prediction, at extremely high energies like that was supposed to be present at the time of Big Bang, the gravity will be dominant, and graviton produce particle and antiparticle pairs, just as photon does. That is, photon at high energies produce the pair production, that is, the electron and positron pairs. Just like that, at very high energies, this graviton can produce the particle and antiparticle pairs. So the second type of force is the electromagnetic force. Initially, the electromagnetic force was two different fields, electrostatic force and magnetostatic force. We have studied that Coulomb formulated the Coulomb's law in 1785, and it is the foundation. This Coulomb's law is the foundation of the electrostatics. That is, by the Coulomb's law, F is equal to 1 by 4 pi epsilon 0 q1 q2 by r square, and this force can either be attractive or repulsive, depending on the sign of this q1 and q2. And later in 1820, Ørsted showed that the current produces magnetic field, or the current carrying material can deflect a magnetic material. In 1831, Faraday demonstrated that moving magnetic field produce electric field. That is the Faraday's law. As per the Faraday's law, we have studied that del cross E is equal to minus dou B by dou T, that is changing magnetic field produces the electric field. Later, Heinrich Hertz showed that the changing electric field produces light or electromagnetic wave. Between 1886 and 1888, Hertz conducted several experiments and he produced this changing electric field, and hence the changing magnetic field. They can produce the electromagnetic wave or light, and he could detect it experimentally. And the Maxwell's equations, and later by the emergence of the relativity, the relativistic electrodynamics, both confirmed the electricity and magnetism are closely intertwined, and it's really two aspects of a single object or a single phenomena called electromagnetism. Almost all forces in our daily life are electromagnetic in origin, like the frictional force and like that. The carrier of the electromagnetic force is photon, which have zero mass and spin 1. Since the photon has zero mass, they also have the range of infinity. That is, they can reach anywhere in the universe within no time. Even though electrostatic force affects only charged particle, electromagnetic force can affect neutral particle also if it has non-zero magnetic moment like neutron. Since this is the electromagnetic interaction, both electric interaction and magnetic interaction is there. If it has a non-zero magnetic moment, they can be interacted by the electromagnetic force. It affects almost all particles except neutrino and graviton. The third force, the force which was put forwarded by the Enrico Fermi in 1933, that is the weak interaction. They have a short range or the shortest range of the order of 10 raised to minus 17 meter. That means two particles can be interacted by the weak interaction only if they are within this distance of 10 raised to minus 17 meter. Initially, in all weak interactions, neutrinos were observed, and the scientists assumed the neutrinos as a trademark of the weak interaction. But later, they could observe a lot of weak interactions in which there were no neutrino emission. The probability of this interaction is very less compared to the strong interaction and electromagnetic interaction. Very less. The carriers are the massive W plus, W minus and Z0 and is called weak-ons or intermediate vector bosons, having heavy masses in the range 80 to 100 GeV, so much larger mass. We know that even the nucleons, the protons and neutrons, having only nearly some 900 MeV or like that. So compared to that, these weak-ons have thousands times masses of the protons and ten thousands or times like masses of the protons and neutrons. So much heavier particles. That is why they have the shortest range of the minus 17 meter. Since the carrier is the so much larger one, it cannot move so easily. In 1960s, it was proposed that the weak interaction and electromagnetic interaction are again part of a more general interaction known as the electroweak interaction. And this theory is called electroweak theory or Weinberg-Salam theory. As per this Weinberg-Salam theory, the electroweak interactions are carried by 4 bosons, one positive, one negative, 2 neutral, that is W plus, W minus, Z0, these are the weak-ons, and photons. In the region of high energies, that is the energy greater than 100 GeV, these carriers become similar to each other, and at moderate energies, this similarity is broken and 3 of them remains massive and the other one remains massless. That is this W plus, this W minus and this Z0. These are the weak-ons. The weak-ons remains massive and this photon becomes massless. So this is the electroweak theory or Weinberg-Salam theory put forwarded by or formulated by these scientists. And by the experimental observation of this W plus, W minus, Z0, later it is accepted as as the electroweak theory or the electroweak interactions are really the general interactions which is The fourth one is the strong force. That is the force experienced between nucleons or force inside the nucleons. Combines this. It is the strongest electromagnetic force among the four fundamental forces or four fundamental interactions. The range of the order of 10 raised to minus 15 meter. Here again, the carriers are assumed to be the mesons of having the mass of 100 MeV. That is why this short range of the order of nuclear distances. Initially, the origin of this force was assumed to be due to the meson exchanges between the nucleons, known as the Yukawa's meson field theory. We will discuss this Yukawa's meson field theory in detail later. Later, it was understood that this strong force is really the remnant force of the real strong force between quarks carried by gluons. So, in reality, the gluons are the carriers. Temporarily, we take the mesons are the carriers, but really the gluons are the carriers. And the real strong force is between the quarks. Now we can compare the different four basic forces or basic interactions. In terms of relative strength, you can see that the strong is the strongest one. Compared to this one, electromagnetic force has only the strength of 1 by 100th part, and the weak force has so much weak that it has only the strength of 1 by 10 raised to 13, and the gravitational force is the weakest and feeblest one, which has the relative strength of 1 by 10 raised to minus 39 compared to the strong force. So this strength is determined by the cross section, the probability of interaction between two particles, and their average life, like that. Like considering those parameters, this is determined, this relative strength is decided. And in terms of range, the strong force have the range of the order of 10 raised to minus 15 meter, but electromagnetic force has infinite range and gravitational force has infinite range, but the weak force have the range of the order of 10 raised to minus 17 meter. We know the reason why this range. The mesons are the carriers of the strong force. Photons are the carriers of the electromagnetic force, and weakons are the carriers of the weak force, and graviton is the carrier of the gravitational force. Since this graviton is massless, it has infinite range. This is so much heavily massed. This weakons is heavily massed. The masses of the order of 100 GeV or 100 GeV or 10 raised to 5 MeV. The weak force have the shortest range, 10 raised to minus 17 range. And again, the photon is massless. Since the photon is massless, electromagnetic force has infinite range, and the meson is somewhat massive. The strong force have the range of 10 raised to minus 15 meter. And you can see the spins of the carriers. The mesons have the spin 0, photons spin 1, and the weakons again with spin 1, and gravitons are with spin 2. You can notice that all the spins of these carriers is integer spins, means all are bosons. All these carriers are bosons. Now we can classify the particles based on the forces affected. When the forces, the particles affected by the strong force is called hadrons. Hadrons can be fermions or bosons, means hadrons may be with a half integer spin or whole integer spin. The hadrons with half integer spin or fermionic hadrons are called baryons, and bosonic hadrons are called mesons. The examples for the baryons are these nucleons, that is proton, neutron, then this lambda, then this sigma, then this psi, then this omega. And the examples for the mesons are the pi and these kaons and this eta. And the particles unaffected by the strong force is again of two categories. There is no common name for them. The fermionic particles which are unaffected by the strong force is called leptons. Examples are the electrons, muons, tau particles and their neutrinos. Then the bosonic particles which are unaffected by the strong force are these carriers, generally the carriers, that is the photons, W plus W minus Z0, and you can add here gluons and the graviton. They can also belong to this category. Okay, thank you.